everybody. So now we're going to move on to another topic which is closely related to our discussion of isomorphisms and factor groups. And in some way, this topic is designed to tie a lot of these ideas together. And what we're going to do is we're going to generalize our notion of isomorphism to a concept called homomorphism, which is a function which is almost an isomorphism, but isn't bijective. And this is going to give us a very powerful tool to understand the relationship between groups and the connection between factor groups and subgroups and maps between groups. So let's start with the definition. So suppose you have two groups, G and H. A homomorphism, phi, from G to H, is a function which has the property that it changes the multiplication in G into the multiplication in H. So the way to read this, we've seen this equation before. It's the same equation that came up in isomorphisms. And it says that if you multiply two elements together in G and then apply phi, so you end up in H, that's the same as if you had first applied the function to both G1 and G2 and got two elements of H and multiplied them in H. And this is exactly the same property that we introduced in the notion of isomorphisms. The difference is, for an isomorphism, we also required that the map be bijective. And for a homomorphism, we relax that condition. We just require the multiplicative property, and we don't worry about whether it's bijective or not. So if you have a homomorphism, which is bijective, then that's what we called an isomorphism earlier. So two groups are isomorphic means that they are basically exactly the same. If you have a homomorphism between two groups, it gives you a partial relationship between their structure, but not a complete identification. So let's look at some examples. And these are all things that we will have seen before, but we'll now have new language for them. So the first example is, suppose our group G is the symmetric group on n elements, and our group H is just Z mod 2. And our map, our homomorphism, is going to define phi of sigma to be 0 if sigma is an even permutation and 1 if it's an odd permutation. And this is going to turn out to be a homomorphism. So why is that true? So the condition to be a homomorphism is that phi of sigma 1, sigma 2 is supposed to equal phi of sigma 1. And now, because this is an element of the group Z2, I'm going to write it additively. So we write the condition for multiplication in the symmetric group multiplicatively, but in the Z mod 2, we traditionally write it additively. And so our homomorphism equation looks like this. So is this true? Well, if you think about this, there's really four cases, because phi of sigma, this phi only depends on whether the permutation in question is even or odd. And similarly here and here. And so there are four possibilities. Sigma 1 and sigma 2 can both be even. Both one can be even and one can be odd. Or they can both be odd. And in this case, of course, sigma 1, sigma 2 is even. Odd, we've seen this a million times. Odd, even. And phi of sigma 1 is 0, 0, 1, 1, because it's 0 if sigma 1 is even and 1 if it's odd. And phi of sigma 2 is 0, 1, 0, 1. And phi of sigma 1, sigma 2 is 0, 1, 1, 0. And if you look at this table, you see that in fact this column, phi of sigma 1, sigma 2, is the mod 2 sum of the first two columns. 0 is 0 plus 0, 1 is 1 plus 0, 1 is 0 plus 1, 0 is 1 plus 1 mod 2. So the fact that this is a homomorphism is just an expression of the fact that we know that an even times an even is an even times an odd is an odd. And so we have this relationship between the two groups, which is given by this homomorphism, which captures what we know about even and odd permutations. Here's another example that we've seen many times. Suppose that we take the group of invertible 2 by 2 matrices, and we let H be the multiplicative group of real numbers, And our map is just the determinant. And this is also a homomorphism. And that's just an expression of the fact that if you take the determinant of a product of two matrices, it's the product of the determinants. And so that's a well-known fact from linear algebra, or if you doubt it, you can work it out using the formula that the determinant of a 2x2 matrix is AD minus BC. So these are both real numbers, and this just says that if you want to know the phi here is the determinant. So I could have just written determinant. If you want to know the determinant of a product of matrices, it's the product of the determinants. Now, of course, this sort of indicates how far this is from an isomorphism. This group here is much bigger than R star, and also it's non-abelian. And so this can't be an isomorphism, and similarly in the earlier case, but there is still some structure in GL2R that you can find via the determinant map. Here's another really important example. Now I'm going to let H be any group, and I'm just going to pick an element of H, and I'm going to define a function from the integers to H. So this is my group G, it's the integers. And the function is phi of n is H to the n. So, I mean, you could take any example that you want. I mean, if H were, for example, Sn, I could choose H to be maybe the permutation, let's say n is big. And I just take the permutation 1, 3, 5, 7, 9. Then I define phi of an integer to be H to the n. So phi of 0 is the identity, phi of 1 is H, phi of 2 is H squared, and so on. And phi of, in this particular case, since this is a 5 cycle, phi of 5 is going to be H to the 5th, phi of 8, well, it's H to the 5th, which is the identity. So this isn't an isomorphism because phi of 0 is also the identity. It can't really be an isomorphism because multiple powers of H only give you 5 different elements. But it is a homomorphism because phi of n1 plus n2 is H to the n1 plus n2, which is H to the n1, H to the n2. And we'll see more of this later, but if you think about this for a minute, what's really going on here is that the image of this map, that is to say, the things that you hit by this, is exactly the cyclic subgroup generated by H, little h, inside big H. So typically this map is not going to be either injective or surjective, but it is still a homomorphism. And this is really the key property here. And then let's look at one more example. Here, both of the groups involved are abelian. Our group G is the real numbers, and our group H is the group of complex numbers of norm 1. So the group operation on R is plus, and the group operation on T is times. And our map is this cis map. It's the map cosine R plus I sine of R. And for those of you who may have seen this before, you can also write this as e to the IR, where using the complex exponential. But we don't need that for this. It makes some of the arguments easier, but it's not necessary. So what does it mean for this to be a homomorphism? Well, we need to know that phi of R1 plus R2 is phi of R1, phi of R2. In other words, that cis of R1 plus R2 is cis of R1, cis of R2. Now, this is the kind of the fundamental property of the cis map, and we've seen it before, but just to sort of make it completely obvious what's going on, cis of R1 plus R2 is cosine R1 plus R2 plus I sine of R1 plus R2. And cis of R1 times cis of R2 is cosine R1 plus I sine R1 times cosine R2 plus I sine of R2. And if you multiply these out, you get, for example, cosine R1, cosine R2, minus sine R1, sine R2, plus I, this is in the real part, cosine R1, sine R2, plus sine R1, cosine R2. And by the addition laws for sine and cosine, these two things here and here are equal. So this is a homomorphism. And that's going to do it for this collection of examples.